Let me just give you a brief overview of what we had learned in the last lecture, and based on that we'll develop in this session also. We basically developed an equation which was an energy balance equation, and according to the equation it says that En, that is energy coming into the system, whether it is in the form of heat, work or mass, minus E out, again the three forms, would result in the change in energy of the system. I'm sorry, this is. Can you understand what is written on the slide? So this is the basic equation that we had looked into. Uh, and we saw an example which relates the energy in and energy out and the change in energy of the system. The example basically related the heat and work coming into the system and going out of the system, and as a consequence of that the change in internal energy of the system was evaluated. This is one form of the equation that we had looked into. We had also seen various forms of the same equation, where we said that if you're dealing with changes with respect to time, we would have essentially the rate at which energy is coming into the system minus the rate at which energy is leaving the system, and this would be equivalent to the change in energy of the system with regards to the time. This is what is another form of the same equation. So we have seen one numerical equation. We'll see a couple of more examples and see how this energy balance equation can be applied to different situations given to you, depending upon the data that has been given to you and depending upon what has been asked from you. So this example of the radiator tank we have already seen. We'll start with another example, which is this example. It says that a fan consumes 20 watt of electric power. So this is the electricity that the fan is consuming when it is to discharge air from a ventilated room at a rate of 0.25 kg per second. So the rate at which the air is being discharged from, and the velocity of the air at which it is being discharged is 8 meters per second. We have to determine that whether this claim is reasonable or not. This is what we have to do. Can somebody, before we begin with the solution, can somebody give me an idea how should we approach this problem? No one? Anybody could give me an idea or a suggestion how to start working on this problem?
सर डेटा को नोट करके कोई फॉर्मूला वगैरह देखते हैं कि जो एप्लीकेबल हो सकता है, तो इस तरह चेक करेंगे कि क्लेम सही है नहीं है.
Alright, तो आपकी अप्रोच ये है कि first note down the data and then you try to see which equation can actually fit into this problem. Although it's not desirable.
सर मैथ्स पर
जी जी
सर मैथ्स फ्लो रेट को वेलोसिटी स्क्वायर से मल्टीप्लाई करेंगे तो फिर
all right, let's see. Mathematically you are approaching, obviously you have a reasonably correct approach with regards to mathematics concern, but we have to understand the physics before we could apply it mathematically. Let's try to understand the physics first. First thing, we have this schematic with us, and the schematic says that this is my system. This fan is my system, which includes the motor and the fan itself. So what is being supplied to this system? Can somebody tell me what is being supplied to the system?
Electricity.
Electric power.
Yes, yes. So a power of 20 watt is being supplied to this system, coming into a system, and as a result of this, the air is leaving the system at a velocity of 8 meters per second, and the rate is also given, and the mass flow rate is also given to you. So this is basically leaving the system. Obviously, this is an closed system. Yes? Yes, no? Is this a closed system or an open
सर
system?
क्लोज कैसे होगा सर? मास एंटर भी कर रही है और लीव भी कर रही है.
Open system.
ओपन है.
So that's what I am asking you. This is an open system. That means the air is leaving the system. Even if the criteria is that mass should flow into the system or it should flow out of the system or both. So since the air is leaving the system, you already know that this is an open system problem. And let's move on with the understanding of the problem a little further. We'll start with two assumptions. One is that the air which is initially entering into the room or air which is essentially part of this system is having negligible velocity. So we can ignore the velocity of air as being part of the system or is coming into the system. The second thing, it's a steady state process. That means applied to the system is essentially consumed in accelerating the air to a velocity of 8 meters per second. What does that indicate about the energy of the system or change in energy of the system?
सर 0 के इक्वल होगी.
Change in energy of the system with regards to or with respect to time would essentially be 0. All what is coming in is going out in terms of air being accelerated. Is this clear?
स्टेडी स्टेट प्रोसेस की वजह से 0 होगा ना?
Yes, exactly. Steady state process की वजह से 0 होगा. We'll see the equation in a minute's time. All right. So if we look deeper into the process, we see that there are energy conversions that are being involved. First, the motor of the fan, which is taking the electricity, converts the electrical power to the mechanical shaft power. That means this electrical power is used to rotate the shaft of the fan. And the fan blades, they are made in such a way that a large fraction of the mechanical power of the shaft is basically used in mobilizing the air. This is actually what is happening. But in the limiting case, we assume the ideal case. Ideal case is which case? Where there is no loss of the energy that is coming in. That means the electrical energy which is converting into the shaft and the mechanical energy which is being converted into the kinetic energy of the air, both of them, they do not contribute toward any. All right. Is this point clear? Is the point clear?
Yes, sir.
All right. And this process is working under steady state. Steady state means since whatever energy is coming into the system is being consumed by the air, there is no change in energy of the system with regards to time. So the statement is that electrical power input would be equal to the rate of increase of kinetic energy of the air. When we apply the energy balance, now since we are given the data in terms of rate or power, we'll apply the power equation, which says E dot in. What is E dot in this case?
Electrical power.
Electrical power. And what is E dot out?
The increase in the kinetic energy of the air part.
Yes, the rate of increase of the kinetic energy of the air. And what is dE system by dt, the change in energy of the system with regards to time? What is this value?
0.
This is 0. Why? Because you are talking about a steady state process. For a steady state process, the energy of the system is not changing with regards to time. So what essentially you will have would be the power coming into the system. It would be consumed by the kinetic energy of the air. Is this point clear? So what we were discussing, we discussed that the power coming into a system in terms of electrical power is equivalent to the power imparted to the kinetic energy of the molecules, air molecules. So this is the situation where you have, where is it? This is electrical power coming in. You are familiar with the electrical power, it is given to you. This is mass flow rate of the air multiplied by the kinetic energy per unit mass. Why I write the mass flow rate with specific kinetic? Because mass flow rate has the units of kgs per second, and specific kinetic energy is essentially kilojoules per kg. So if these two cancel out, I would essentially have kinetic energy in kilojoules per second, which is essentially the power, so that we could equate the electrical power with the power associated with kinetic energy of the air. Is this point clear? Now we just have to plug in the values, and once we plug in the value, we see that the velocity comes out to be 6.3 meters per second. This is the velocity of the air in the ideal case that we have calculated. Now, if we go back to the question again, we have the answer that we require is whether the claim made by the manufacturer, is it reasonable or is it not, based on your calculations? Can you comment on that?
No, sir. Velocity different.
Different. Let's say my the manufacturer claims that the velocity of this fan is 6.3 meters per second, which is the same that you have got as per your calculation. Then whether the claim would be reasonable or not?
Yes.
सर तब भी रीजनेबल ना होता क्योंकि ये हमने जो है वो एक मतलब एक कंट्रोल्ड एनवायरनमेंट के लिए हमने कैलकुलेट किया, तो नॉर्मल एनवायरनमेंट में इससे जरा डिफर करेगी वैल्यू.
ज्यादा होगी कम होगी? It would be more or less?
Sir, I think it would be less.
All right, Taha, have you got the point? Taha Firas. Taha, are you there?
Yes, sir.
So did you get the point?
Sir, the internet is not not that much good, so I didn't listen
All right.
everything.
All right. So you have a recording. Kindly go through the recording and let me know if you have a problem in the next class. All right. So as one of you mentioned that even if the manufacturer claims the velocity to be 6.3 meters per second, which is the answer we got, the claim would still not be reasonable. Why? Because if you see, we had considered the ideal case. In an ideal case, we say that there is no losses of energy in the conversion process. Electrical energy is converting into mechanical energy, and that mechanical energy is converting into kinetic energy. In the conversion process, there is no thermal energy generated. If there would be thermal energy generated, the eventual velocity that we'll get would be less than 6.3 meters per second. So this even if the manufacturer claims it to be 6.3 meters per second, which is an ideal case, it would be very highly unlikely to believe that the claim is correct. Clear enough?
Yes, sir.
All right, moving on, we have another example in which it says that a room is initially at the outdoor temperature of 25 degrees centigrade. Now a large fan that consumes 200 watt of electricity is turned on, and the rate of the room and the outdoor air is governed by this equation. Q dot is the heat transfer rate, U is the heat transfer coefficient, which is 6 watt per meter square degree centigrade, and area is 30 meters square through which the heat transfer is taking place. Ti and T naught basically represents the inside temperature and outside temperatures. We have been asked to determine the indoor air temperature when steady state operating conditions are established. So how should we start solving this problem, or what should be our approach to solve this problem?
Steady state system है तो
जी, steady state system है तो
internal
sorry,
change in internal energy will be equal to zero. Change in energy of the system will be equal to zero.
change in energy of the system with regards to time would be zero. When you are talking about steady state operation, always remember steady state is associated with time. Change in energy of the system with regards to time would be essentially zero. All right, be mindful of that. So before we begin, we'll start with the basic model as we have done in previous problems. We'll look into the basic model. The model says that the power coming into the system, which is the electrical power, this is essentially how much it is, 200 watt, which is coming into the system. And as a result of that, the temperature of the room gets higher, and there is a heat transfer that is taking place due to the temperature difference between the uh, system and the surrounding. System is your room and surrounding is at 25 degrees centigrade. Now if I have to solve this problem, I'll basically start with these two simpler assumptions, which says that heat transfer through the floor is negligible. So that means whatever the heat is transferring, it is governed by the equation given to you, and there is no other energy interactions involved in the process. So based on this, if we try to solve the process, we say that room gains energy as a result of the power being consumed by the room. As the result of this energy gain, the air temperature within the room tends to rise. As the temperature of the air rises, there is a heat loss from the room to the surrounding until the heat loss equals the electrical power consumption. At that point, the temperature of the room of the air and thus the energy content would remain constant. That is, the steady state process would start to take place. So the conservation of energy for the room then becomes that you have what is coming into the system, electrical power. What is going out of the system? It is the heat transfer or heat in form of heat transfer going out of the system. And change in energy of the system with regards to time would be what?
Zero.
This would be zero since you're talking about a steady state process. So again, your energy in would essentially be equal to energy out. Now, I would like you to kindly solve this problem and find out the temperature of the room once you have established a steady state condition. Do you have the notebooks with you? Do you have
Yes, sir.
All right. Kindly solve this problem and find out the indoor temperature when the steady state conditions have been reached. I'll give you 2 minutes. Kindly solve it out so that I can proceed further. If someone is having a problem, he can also ask me if there is a problem. All right. Currently or not. So E in minus E out. E in would be what? It would be the electrical work coming into the system, and it would be expressed in terms of per unit time, which is power. And Q out, or the rate of heat transfer, is basically expressed by the equation where UA. So electrical work in is basically 200 watt, and U is already given to you. I guess it is 6. Area is given to you. I suppose it's 30. The value is 30 meters square, yes. And you have the final outside temperature given to you as 25 degrees centigrade. Once you plug into the values, you'll find out that the inside temperature would be essentially 26.1 degrees centigrade. So at steady state conditions, this is the inside temperature at which the heat is being transferred to the surroundings according to this equation. Is it clear?
Yes, sir.
All right. Moving on.
एक मिनट
जी, 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 जी.
देखने दें.
You'll get the slides, you'll have the recording, you don't need to write it down.
Okay,
You
sir.
just understand at the moment. Clear? Should I move ahead?
Yes, sir. Clear.
Yes, sir.
All right. So this is the third problem that we have, and I would like you to kindly attempt this problem. The problem says a very simple problem. The problem says that the lighting needs of classroom are to be met by 30 fluorescent lamps, and each lamp basically consume 80 watts of electricity. Obviously, the light in the classroom are to be kept on for 12 hours a day and 250 days a year. For a unit electricity cost of 7 cents per kilowatt hour, determine the annual energy cost of lighting for this classroom. So you have to find out or attempt for this first part of your problem. Then we'll come on to the second part, which says the effect of lighting on heating and air conditioning requirements. We have to discuss upon that. So if I ask you, how would you start solving this problem? How would you start with this problem?
Yes, sir. 30 lamps हैं, each consuming 80 watts. तो total हो जाएगा 2400 watts
Yes. So
electricity.
first of all, yes, great. So first of all, you have to start with the light. Light power is basically the power consumed by one lamp multiplied by the total number of lamps. That is the total power consumed or the total power requirement for that room. So this comes out to be 2400 watts or 2.4 kilowatts. So this is the lightning requirement or power requirement for that one room. Now, what should be the second step?
Sir, 12 hours a day. 12
Sorry?
hours a day use हो रहा है. 12 hours a day lights on है. तो it means कि 2.4 kilowatt into 12 ये एक day की power consumption.
All right. Can you explain it in English, because I suppose Taha
Yeah.
is also listening, so it would be
Okay.
convenient. All right. Thank you. Yes.
The lights are switched on for 12 hours. So and we know that all 30 lights are consuming 2.4 kilowatts. So
Yes.
if multiply 12 with 2.4, we'll get the energy consumption for one whole day.
All right.
सर 12 आवर्स तो मतलब एक डे का हाफ है, तो 0.5 से डायरेक्ट मल्टीप्लाई कर दें 250 को, मतलब 12 आवर्स का डे है ना, तो इसकी जगह पे अगर हम 0.5 डे कंसिडर कर दें एक को, मतलब 2 डेज को, अगर इसी तरह मतलब आपको समझ लग गई होगी.
I am coming to that. I'm coming to that. You have first calculated the power requirement in terms of wattage. Clear? Now you have, I mean, this is 2.4 kilowatt means 2.4 joules per second. All right. This is what is meant by kilowatt. Is it?
Yes, sir.
Now, what you want to calculate is basically, since your concern is how many kilowatt hours are required for the year. So you have to calculate the total time for which this lightning power is required in terms of hours. So it's easier if I could find out the total number of hours those lights would be on or those lamps would be on in that room for the year. Clear? If I calculate the operating hours in terms of hours for that matter, that is 12 hours a day multiplied by 250 days a year, I would have this lightning power required for 3000 hours in an year. Clear enough?
Yes, sir.
Yes, sir.
All right. Now I can calculate the total kilowatt hours. So the total amount and cost used per year become lightning energy in terms of lightning power multiplied by the lightning operating hours. This would be 2.4 kilowatt multiplied by 3000 hours per year would give me 7200 kilowatt hours per year. This is required for an year. Clear enough?
Yes, sir.
Yes, sir.
Now, if I have to determine the energy cost, it's very simple and basic maths, but how would you do that?
So you will multiply it with 7 cents per kilowatt hour, so you have 7200 into 7.
Very good. Simple enough. you know the price of 1 unit, which is 7 cents. So for 7200 units, which is 7200 kilowatt hour, you just have to simply multiply the requirement with the rate for a unit of electricity, which is a unit of electricity is basically kilowatt hour. So 7200 kilowatt hour per year multiplied by $0.07, sorry, which is 7 cents, would give you that $504 are required per year to maintain this load for one classroom. Clear enough?
Yes, sir.
This was very easy and simple. Now, the important thing is I want you to discuss or tell me what would be the effect of this load in a classroom on the heating and air conditioning requirements of that room.
सर हीटिंग की रिक्वायरमेंट कम हो जाएगी और एयर कंडीशनर की रिक्वायरमेंट ज़्यादा हो जाएगी.
All right, can you explain it in English?
The heating, the requirement for heating would decrease and the requirement for air conditioning would increase.
Very good. Thank you. Who is this?
Sir, Mohammed Shazib.
Shazib. Shazib, very good. Yes, this is the amount of energy which is converting electrical energy into light. And you all know that this would ultimately convert it into the energy of the system. That means this amount of energy per second would be stored in the room. And if I assume that the room is well insulated and there is not much energy losses from the room, the heating requirement would decrease by this much amount, which is 2.4 kilowatt. And similarly, since air conditioning is done to cool down the room, the air conditioning load would increase by the same amount. Is this point clear? Is the point clear?
Yes, sir.
Yes, sir. Yes, sir.
All right. As it is that light ultimately converts to thermal energy of the system, and if we disregard the energy loss from the windows, we would see that 2.4 kilowatt of electric power eventually part energy of the classroom, and the heating requirement would reduce by the same amount, whereas the air conditioning requirement would increase by the same amount, which is 2.4 kilowatt hour. I hope this makes sense and this is clear to you.
Yes, sir.
Yes.
All right. What I'll do is here and we'll have a minutes and then we'll begin with the session again. All right.
Okay, sir.
All right. So